Okay, in this video, I want to discuss the E2 mechanism. And here are some important concepts I want to cover before we start going into examples. So the E2 is just like SN2. It is concerted, it is one step. What are we doing in E2? We are making alkenes. Just like in any other elimination reaction, we're just making alkenes. We're making double bonds. The beta proton that we will be removing with our base are strong based. So I'll write that too. So strong bases. We are using strong bases in E2, such as sodium hydroxide. That's a good one. So we're making alkenes. The beta proton, this is what trips a lot of people up. The beta proton must be anti-periplanar, which is 180 degrees to the leaving group. Now, I will do an example that illustrates this point, so there's nothing to be worried about. Also, we favor E2 by strong sterically hindered bases such as LDA, lithium, I don't know, diamine, I don't know. It looks like this. Lithium, so we have the lithium is right here. We have a lone pair, and when we remove this lithium, we'll see that there's a lone pair right here, and that will give this guy a negative charge. So it's strong and it's sterically hindered by these two groups right here. And tert butoxide looks like this. We have an O minus that looks like this. See how it's sterically hindered? And that favors E2. So yeah, let's start doing some examples. Okay, let's do an example that illustrates E2 reactions. So let's say we have a, come on, work with me, a tertiary alkyl halide. So this carbon has 1, 2, 3, so it's tertiary. And we should know that SN2 does not occur on tertiary carbons. So we should be thinking SN1 maybe, E1. Well, if we look at our base, it's strong. So that's going to be E2. So strong base equals E2. Okay, so this carbon right here in the center is our alpha carbon, the one directly connected to our leaving group. And these carbons that are connected to it are our beta carbons. And they are all the same in this case because this molecule is symmetrical. So I'm going to erase those, and now I'm going to draw in our hydrogens so we can see what's happening. So I'm going to remove this cation so it's easier to see. So put a OH right here. So what's going to happen is this base is going to take a proton, and these electrons on this proton, this hydrogen carbon bond, is going to be shifted right here to make a double bond. And that is going to kick off our bromine. This is concerted, it's one step. E2 is concerted, so concerted. We are not having a carbocation, none of that happens. It all happens at once. So we'll get something that looks like, hold on, looks like this. Now if you say remove this proton up here, you would get something that looks like this. Remove this proton, you would get something that looks like that. But if you look closely, all these molecules are the same if you rotate them. So you would only want to draw one of these. So that would be your only product. The reason why it's not SN2 is because it's too sterically hindered for it to be SN2. Tertiary carbons, E2 can happen. Yes, E2. In fact, E2 can works on tertiary, secondary, and even primary carbons. It works on all of them. Now let's do an example that illustrates anti-periplanar. Okay, now let's do an example illustrating that anti-periplanar requirement. So anti-periplanar. which is that 180 degree thing. The D here is just deuterium. So deuterium, I may have spelled that wrong, but it's just an isotope of hydrogen. So isotope of hydrogen. The reason why I have deuterium here is to illustrate which proton we are removing. So it's easier to see if I remove the D, the dashed, or the wedged one, depending on if it's anti-periplanar or not. So the way we find out if it's anti-periplanar or not is we draw the chair conformation. Makes everything a much more visually pleasing, really, to see what's going on. So I'm gonna draw the chair. Okay, so this chlorine, we'll label that number 1, 2, 3, 4, 5, 6. In this position right here will be number 1. We see our chlorine is wedged, so it will be axial up. And there's a hydrogen branching off of it. I'll draw that in just for the heck of it. So number 2, right here, deuterium is wedged, so we'll have equatorial up. And a hydrogen is axial down. This guy right here is our 6th position because 1, 2, 3, 4, 5, 6. Hydrogen is facing up, so it's equatorial. Deuterium is facing down, so D. Okay, now chlorine is our leaving group. We have to have protons that are anti-periplanar to it. So from here to here is that 180 degree periplanar requirement. So our base, which is sodium tert butoxide, will come in and take this proton and push those electrons right here. It cannot grab this deuterium because that is not 180 degrees. So this is 180 degrees. If we look on this side, it can't grab this hydrogen because that's not anti-periplanar, but this deuterium is anti-periplanar because look, this is down and this is up 180 degrees. Okay, so let me erase this stuff. So let me draw in our sodium ethoxide. I'm just gonna get rid of the, not ethoxide, sodium tert butoxide. There's that. Remove that sodium ion so we see what's going on. So this guy is going to grab this proton and it's going to shift these electrons right here to make a bond right there. So what that's going to look like in our hexane ring is something that looks, that's horrible still, but let me make a better one. Maybe a little bit better. Anyways, so these guys are still okay. They're still wedged and dashed because we didn't do anything with those just yet. Not yet. Just not yet. Okay, so deuterium, hydrogen. Chlorine has been expelled. When we made that double bond, this chlorine atom was expelled. So we have nothing here. We have a double bond here. We removed this hydrogen, so this guy is no longer here, but our deuterium is. That is no longer wedged because this bond right here is, let me show this, this bond right here causes this to be trigonoplanar, so we just represent that by a stick. So that would be one of our products. Now let's draw our other product. So I'm going to draw that chair configuration again. So let me put plus right there. Let me draw it right here. Okay, chlorine here, hydrogen, hydrogen, deuterium, deuterium, hydrogen. So this group, this atom is anti-periplanar to this, so it's going to work. So we'll take another molecule of tert butoxide. So I'm trying to think where to put this. Put this right here. There we go. So this guy right here will act as our strong base, take that deuterium, push these electrons to make a double bond, and expel this chlorine atom. So we'll get something that looks like this. Now we did not mess with these guys, so they're going to stay the same. So we have a dashed hydrogen. wedged deuterium. Chlorine is now gone. We have our bond right here, but we took the deuterium. We still have our hydrogen, so this is going to be right here. Keep in mind this is a stick because it's trigonoplanar, and these would be your two products. Now let's see here, what should I go over? Let's do some more examples on E2 reactions. Okay, let's do a tricky problem. So let's look at this molecule right here, where we have a bromine wedged on this carbon. And let's react it with sodium hydroxide and THF. That's just our solvent. Anyways, so let's do E2 first. So let me draw this bigger. So bromine's here. Let's label our alpha position right here. We have beta 1, beta 2. Reason why this is beta 1 is because this is different than this one because they're not the same betas. This beta has a methyl group attached to it. This has nothing attached to it, just hydrogens. So we have our 3 hydrogens here. And let's react at this first beta position. So let's take our hydroxide, take a proton, shift these electrons to make a double bond, and we'll kick this guy off, this leaving group off, to give us a product like this. Okay, so let's do our second one. Bromine wedged. We will react at our other beta position with our hydroxide anion. We'll take that proton, shift these electrons to make a double bond, and kick off our leaving group. So we'll get something that looks like that. Now you would be thinking that these are our two products. Well, it turns out there is another product. Keep in mind, these are sigma bonds, so they are freely rotating. So at one point, we could have something that looks like this. See here, how many carbons we have? 1, 2, 3, 4. 1, 2, 3, 4. So bromine right here. And we will take our strong base, react it at this beta hydrogen, take that proton, shift these electrons to make another double bond, and what we'll see here is we will get a cis alkene. Also, remember, SN2 is in competition, so we will have a SN2 reaction. So let me write SN2 for this guy right here. So we have our bromine plus our OH. This is SN2, so we do a backside attack. We'll kick off that bromine, and we'll get an inversion of configuration. So a dashed OH. So this is SN2 right here. So if we look at these three right here, which of these is more stable? Well, if you watched my first video on elimination, the E1 reactions, you would see that the trans product is more stable. It is the major product of these three. So we have a hydrogen here, hydrogen here, hydrogen here. So that is mono substituted. This is trans, which is di-substituted, so di-sub. And this is cis, which is di-sub. So this would be your major. This would be, I guess, your second major because it's more stable than mono-substituted. But if you ask to draw your major product, this is what you should draw. Now I'm going to do one more problem, which will really hopefully not confuse you because it is tricky. Okay, here is our last example for this video, and it is not really confusing. It just can be a little tricky at first glance. So we're still going to use that same compound we had previously. So here's our bromine, and we'll react it with, what's it called? Let's do it with LDA, which looks something like this. We have a nitrogen, 2 groups branching off like this, and 2 lone pairs. I excluded the lithium, that's what the L stands for, because it's not really important. So this is our negative charge on our nitrogen. See, as you can see, it's very bulky. And we are going to do this in THF. But let's do our elimination reactions. We cannot do SN2 in this case, so SN2 will not occur. So SN2, no, because the base is too bulky. Okay, so here's bromine. We have our hydrogens. So our base will attack one of those protons and it will shift those electrons to here and kick off our bromine like we've always been doing, and we'll get something that looks like this. And we can do our other products that we had from that last page when we use sodium hydroxide. So we're going to get our trans, we're going to get our cis. So we're going to get all these products, but the major product is this. And I'm thinking, no, that can't be. It's less substituted. It's not going to, no. But the reason why this one is favored is because it is on the terminal position and our base is bulky. Since our base is bulky, these hydrogen atoms, these protons, are more accessible. So, bulky base equals more accessible protons. So this would be our major product and these would be our minor products. But we would not have SN2 because this base is way too bulky for SN2 to do a backside attack. So the reason why this is a major product is because our strong base is way too bulky to continually get these protons. It's going to get the more accessible ones, which are on the terminal side. So I hope this video helped you guys. If you have any questions at all, just feel free to leave a comment down below.